Okay, today we will be talking about the variational formulations. So we will first start giving the mathematical backgrounds of it, which helps us to understand better what we are doing here actually. Mathematical backgrounds. Now, let's say that we have a functional so that's the definition of a functional. We have an integral integrated within an interval. A function composed of x, f of x, we have a u and maybe the derivative of that u dx. And in this functional we have another ux is a function defined at the interval a and b. Interval a and b, and f is a known function. Before going further, let's write the definition of what a functional is. Let me write the definition and then we will discuss. It is the collection of admissible functions belonging to a class of functions in function space rather than a region in coordinate space. So let's sit back and try to understand what a functional is. So I think it's better to let's first discuss an integral in the following form, f of x dx, right? Let's say that that's y is equal to integral f of x dx. So what does this integral tells us? We have a coordinate space, right, in x and y, and we have a f of x here, and when we integrate it between a and b, the integral will give the area under that function. Okay, let's not say f of x, let's give something like that. Okay, so that's the definition of a typical function defined in a coordinate space. Now in the functional, instead of a single function, we have collection of functions, right? They belong to a class of functions. So we have f of x, u of x, and maybe the derivative of the u of x, all written or evaluated under that function. We actually use that, right? For example, let's give an example. The total potential energy is a functional. for the static case, for example. When you, for example, think about the bending behavior, bending deformation, the internal energy is an integral minus an external energy. In the internal energy expression, we have the second derivative of u, and in the external energy, we have the function of u itself. So when you combine them, this matches the definition of a functional. So again, let's repeat, is a collection of admissible functions belonging to a class of functions. Okay, so we have more than one functions defined in this functional. Now, the fundamental problem. So what do we want to do with this functionals? Okay, we defined it, but what do we want to do? The fundamental problem of variational calculus is to find a function u of x which gives us the minimum or maximum value of p. Okay, so again, let's think about the total potential energy case, right? So we are trying to find a displacement field that makes this energy equal to, or that makes this energy as minimal. So this was shown by this symbol. So the sentence that I write here is to find the function ux which extremizes p is written as follows. The variation of in this energy when we have a ux is defined as equal to 0, and this symbol is the variation symbol. Okay, now let u of x be the extremizing function so we have a functional defined p, and the function ux makes that p equal to minimum or maximum. Okay, so let's draw it. So we have an interval between a and b. And I have a u of x defined within that interval. And this u of x is the function that gives us the minimum value for p. Okay, so let's make another definition. So let u hat be the family of neighboring paths of u of x, and at the endpoints they coincide. So I can have many u of x functions. One of them could be this one, u hat x. The other one could be that one, right? So the both matches the definitions that we give here. The only important property of u of x, of course, they have to be differentiable. We will talk about that. And also at the endpoints, they have to coincide with the extremizing function u of x. So if we write the equation or the definition of u hat in terms of equations, now that's equal to u of x plus a parameter epsilon and another function. This one is a small parameter nu of x is twice differentiable function with nu of a equal to nu of b, and that should be equal to 0. So this could be any function, right? But it has to satisfy these conditions, which is twice differentiable nu of a and nu of b must be equal to 0. And we can just write this as follows. We have the actual u of x, extremizing function, plus some variation in this u of x. Okay. Now, before moving forward, I want to make a clarification or a definition. Now, variation and differentiation has two different meanings. Okay, I mean clearly different meanings. They are not the same thing. So let's put it as a note. Note that variation and differentiation have clearly different meanings. So let's think about the differentiation. Let's use a different color. Again, let's differentiate u of x. When I differentiate, I take a small piece, right? An infinitesimal piece. And in that infinitesimal piece, I'm looking at this distance is d of x. That distance is d of I. And du will be equal to dy over dx. Is the slope of that little piece is what we call the differentiation. But variation is we give a small change between these 2 points to the whole function. So they have two different meanings. So du here is associated with neighboring point at a distance dx. Okay. But variation in u is a small arbitrary change in u for a given x. Now the properties of variation, let's also very briefly discuss that. Let's say that I have a function u square and I want to take the variation of it. The variation of u square will be equal to 2 times u multiplied by the variation in u. Let's say that I have u plus v. If I want to take the variation of that, that's equal to variation in u plus the variation in v. If I want to take the derivative of the variation of u, that's equal to variation of the derivative of u. And I can apply the chain rule. So variation of u can be represented at del u over del x, variation in x, plus del u over del y, variation in y, and so on. Alright, so let's come back to where we left. So these are the properties of the variation. So we said that u hat is equal to u plus a small parameter times a function. And our aim, let's come back here, our aim is to find a function u which extremizes the functional. So to solve the variational problem, of extremizing p or the function we have in our hands, we consider the following. So we give a small perturbation, right? Small variation to the actual u of x. Let's show it this way. Show it as a function of epsilon. This is from a to b. We have f of x u plus epsilon nu u prime plus epsilon nu prime dx. Okay, the reason of writing is this equation is as follows. Now we know that as epsilon goes to 0, u hat approaches to u. So our u hat function will be get closer to the actual minimizing function. So thus the necessary condition for pi to be an extremum is the derivative of this function as epsilon goes to 0 should be equal to 0. That's the condition. Okay? So if I take the derivative of this functional with respect to epsilon, this is what I see. From A to B, that f over del u hat du hat over d epsilon plus del f over del u hat prime du hat prime divided by d epsilon. Okay, dx. You can just think this one as our u of x, and this one is u prime of x, and we take the derivative with respect to epsilon. Then this is equal to, again from A to B, du hat over the epsilon is nu multiplied by del f over del u hat, okay, plus nu prime del f over del u hat prime dx. So this is the derivative. So for epsilon is equal to 0, we know that u hat will be equal to u, then the epsilon over the epsilon, as epsilon is equal to 0, we have the following relationship: A to B nu del f over del u plus nu prime del f over del u prime dx. All right? So I can rewrite this equation as follows. I should put 0 here. 0 should be equal to, from A to B, nu del f over del u dx plus A to B nu prime del f over del u prime dx. So in this integral, I have nu prime and I want to get rid of it. I have to write this nu prime in terms of nu, so that's why I will be using integration by parts. So I'm just choosing dv as equal to nu prime, which gives me v as equal to nu, and I choose u as equal to del f over del u prime. Then du will be equal to d over dx del f over del u prime. Okay, then this expression becomes equal to nu times del f over del u prime evaluated at points A and B minus from A to be nu d over dx del f over del u prime dx. Okay, now let's take a look at this expression. So while defining the new x, we said that it has to satisfy the boundary condition. It should have the same value at intervals with ux at point A and B, meaning that nu of A and nu of B must be equal to 0. So as you see, with this term vanishes. It's equal to 0 because nu is equal to 0. Let's put a note y, that's equal to 0, since this is the essential boundary condition. And if we gather all the equations together, I have 0 is equal to integral from a to b, an arbitrary function nu multiplied by del f over del u minus d over dx del f over del u prime dx must be equal to 0. That's equation star. So if you take a look at that equation, we know that that's an arbitrary function. So the rule, the requirement for u to maximize this function is actually given in this equation. U must satisfy this equation. Okay? So with these derivations, we obtain what u needs to satisfy. So let's continue. We say that the fundamental lemma of calculus of variation states that for continuous function, let's show it this way, in interval a and b with arbitrary continuous function which vanishes at says that we have a, b, an arbitrary function multiplied with the actual function d of x is equal to 0. This tells me that since nu of x is arbitrary, this function must be equal to 0. So in equation star, we obtain that del f over del u minus d over dx del f over del u prime must be equal to 0. This equation is called the Euler equation, and remember that that is the necessary condition for u of x to extremize the p. Now we will see that when we define the total potential are functional as the total potential energy of the system, this Euler equation, when you evaluate this equation, will give you the equilibrium equations. Okay, so with this approach, we can just obtain the equilibrium equation by right from the total potential energy functional. Okay, now let's continue. Let's define the variation in the total potential energy functional. Okay, so the variation in the total potential energy functional is actually equal to, from A to B, variation in F times dx. Now if I apply the chain rule for the variation of F, that will give me that F over del U, variation in U, plus del F over del U prime, and variation in U prime. Put it into the integral, then I have the following is equal to integral from A to B del F over del U, variation in U times dx, plus another integral from A to B del F over del U prime, variation in U prime dx. Okay, so if I integrate that, I'll obtain the following is equal to, from A to B, variation in U del F over del U minus d over dx del F over del U prime dx. So as you see, I obtained the same equation as this one. Alright, so basically when we have a total functional and we want to take the first variation, we can just take the way I showed in here. We'll just take the variation of the parameters, and then at the end of the day you get the result of the Euler equation here, and then the variation of U here. Alright, and you can just equate that equal to 0 and obtain your solution. You don't have to go over all these calculations. Just take the variations with the rules defined here, and at the end of the day you will obtain your similar equation. So let's write it as a note. So finding the stationary value of P by setting the variation of P equal to 0 is equivalent to finding the extremal value the epsilon equal to 0. So they are the same thing. Okay, we can just take the variation of the parameter in this equation and then we did the same thing. Now what we've seen here is this is an arbitrary function, but this arbitrary function have some rules, right? It has to be differentiable and it has to satisfy or at the boundaries or at the interval that we are looking at, it should give exactly the same value as the extremizing function u. So these are the two rules of this variation. So let's write it down also. If we revisit the integration by parts of equation double star, so let's remember that's equation double star. So we do a integration by parts and we obtain this part. So let's write it down here one more time. That f over del u prime dx is equal to nu that f over del u prime a and b minus integral from a to b nu d over dx del f over del u prime dx. Okay, now let's take a look at this condition. So during the derivation we said that nu a must be equal to nu b and they must be equal to 0. So this is which is the statement of essential boundary conditions. Okay. Now, if we left nu arbitrary, so it could be anything, right? In that case, that f over del u prime must be equal to 0 at a and b. Otherwise, this term will not vanish. So these are the natural boundary conditions. So this is what we did here. Let's repeat. We have a functional, right? Function of f, and we want to figure out the properties of the u, so that makes this functional minimum or maximum. So if we want that, what that function is, we see that that function should be obey this rule, this equation. Okay. Or the other option is at the equilibrium condition, the variation of in the total potential energy function must be equal to 0, and we can use that information to solve the particular problem. So let's summarize. So we have a functional, and if we use that functional for the solution, in our case it's the energy, that's a weak form solution. So the only requirement of this solution is have the function to satisfy this condition. Okay, the solution should only satisfy the essential boundary condition. In between this interval, it can be arbitrary. But if you really want to find out the function, the exact function that minimizes this p, then you have to use the Euler equation, which has the following form: del f over del u minus d over dx, del f over del u prime is equal to 0, and that's the strong form solution. Which we call the classical solution. Now let's make a table. On one side we have the weak form solution, and on the other side we have the strong form solution. So here the equilibrium is enforced in an average sense. Okay. So in principle of virtual displacements, so if we give the variation to the displacements, in other words, variation in the displacements, the Euler equations will give you the equilibrium equations. So in the weak form, the field variable u is differentiated n times, let's say. But when you want to solve the strong form, as you see, u is differentiated to m times, so we end up with a more complicated solution. And finite element formulations, we will see, are based on weak form. And the strong form solution is you have to solve this differential equation, and sometimes you may not get an answer. Okay, so if you think about the simple finite element question that we solved before, calculating the P of a circle, we said that the mathematical model, the one that we use is P over D, right? And with this variational formulation, actually it tells us how to obtain the governing equation. You can just use the functional, and from the earlier equation you can determine the mathematical problem, the mathematical equation, the model that you want to solve. And also in the future we will see that using more intervals, right, with this approach will actually minimizes the error that we will get. So these are the uses of the variational formulation. So we will do more exercise on it, and you will better understand what really this variational formulation is used for.